This is chapter 14, Waves and Sound. In this chapter, we're going to learn about waves in physical things such as water, strings, musical instruments. In later chapters, we'll see how there are waves in optics and light. But all over physics and really in the entire universe, waves are everywhere. Even things that don't appear to be moving in waves have wave-like characteristics. So this chapter is an introduction to the basic properties of waves, and we'll go through some applications of waves as well, especially with regard to sound. So I think you'll find this a challenging but interesting chapter.
All right, so let's look at an animation to help us understand waves. Here we have a bunch of beads connected by springs, and the beads, with holes in them of course, are constricted in their motion through these vertical wires. All right, so this is a good image to help us visualize what's happening with waves. All right, so we've got this line of beads connected with springs, and we're going to move them up and down. You can see that we generate a wave pattern. All right, and we've got these beads that are going up and down, but a wave that's being propagated left to right, and then right to left, left to right. Okay, so we can see clearly what's going on here. We've got the waves. When they hit a boundary, they get reflected. We can do bigger waves. You can see the effect even more. But notice that the interesting thing about these waves is the following. The neat thing is that the beads go up and down, but the beads don't actually move horizontally. They only oscillate up and down. So the beads oscillate up and down, but the wave goes left to right, right to left to right. We can see that we have vertical oscillation, but horizontal propagation of the wave. And that's the main thing to understand from this animation. A wave is a transfer of energy through a medium, the material that the wave is moving in. Mass, or elements of the medium, are not transferred, just the energy. In other words, in the example we just saw, the beads don't actually move from left to right, they just move up and down. The energy moves from left to right. Now the first kind of wave we're going to learn about is the transverse wave. The particles of the medium vibrate in a direction that is perpendicular to the direction that the wave is going. Alright, so going back to the beads, and look at that red dot. The red dot is kind of following one of these beads along its vertical oscillation pattern. Notice that the bead doesn't move horizontally, it only moves vertically. So the direction of oscillation, vertical, is perpendicular to the direction of wave propagation, which is horizontal. Longitudinal waves. The particles of the medium vibrate in a direction parallel to or along the direction that the waves are traveling. So let's look at this and pretend it's a slinky. Alright, so if I grab the left part of the slinky and start an oscillation, I'm going to have this kind of pattern where I have areas of greater compression alternated with areas of lesser compression. Now, the interesting thing about these kinds of waves is they do occur frequently in nature, as we're going to see. But the difference between these and transverse waves is that the oscillation happens horizontally, and the wave propagation also happens horizontally. And if you take a look at a little red dot, I'm going to put a little red dot here. Notice the red dot follows the horizontal oscillation, but the medium still oscillates in place. Every member of the medium oscillates horizontally, but stays in place. The medium doesn't move the entire length of the wave. The energy does. Water waves are a combination of transverse and longitudinal waves. Now, water waves, of course, are the waves that you've actually felt before. Anyone who's gone into the ocean. Those of you who surf have ridden waves. But the neat thing about water waves is that they combine these two types of waves. So let's see how that works. Well, the transverse part is fairly obvious because we know that the water goes up and down like a transverse wave. So there is vertical oscillation. But there is also horizontal oscillation. And so let's say that this cork is floating up here at the top. Well, as the wave goes from left to right, the cork is going to follow the water a little bit, and it's actually going to go around in a circular pattern. And so since circles involve motion that's both vertical and horizontal, water waves combine the two types of waves that we've learned. Now let's talk about the elements of waves. So waves have crests, or the high parts, and they have troughs, or the low parts. And waves also have wavelength. The symbol for wavelength is lambda, and a lambda or wavelength can be measured from equilibrium point to equilibrium point, such as this one, or lambda, the wavelength, can be measured from trough to trough, as in this one, or we could also have lambda measured from crest to crest, and in any of the three cases we get the same length. That's the wavelength. Amplitude. Waves have amplitude, which corresponds to wave height, but the amplitude would be half the total distance from bottom to top, from trough to crest. Half of that distance, indicated by this line, is my amplitude. All right, so waves have wavelength and amplitude, and a greater amplitude means greater energy. Anyone who's surfed knows that a high wave has a lot more energy than a low wave. Okay, so let's look at frequency. We can see these waves going by, some horizontal transverse waves, and they have a certain frequency, which means that a certain number of waves goes through a certain point per unit of time. All right, so keeping our eyes on the blue arrow and the counter in the middle, we're going to count how many waves go by in 5 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so 10 waves went by in 5 seconds. Now, if frequency is cycles per second, or waves per second, can you figure out the frequency for this wave? And you probably already did. You're going to have 2 waves per second. Since you had 10 waves in 5 seconds, that means you have 2 waves per second, because 10 divided by 5 equals 2. And that means that the frequency is 2 hertz. Hertz is always the unit for frequency. All right, now let's talk about period, the time required for one complete wave to pass a given point. Keep your eyes on the black arrow, and let's time a wave, dude. All right, so let's see how long it takes for this wave to go by. The timer's at 1.3. Let's run the wave. Stop. All right, let's go back to where it was. Okay, so that, the timer says, has us at 1.86. So from 1.3 to 1.86, one wave went by, which means 0.56 seconds equals our period t. All right, simple enough, right? So frequency is number of waves per second, and period is number of seconds per wave. Just like in last chapter, frequency is number of cycles per second, period is seconds per cycle. All right, so frequency and period are the elements you have to remember. Now let's talk about wave velocity. Let's suppose that we have a train, and that 2 cars go by in 1 second. All right, so 2 cars go by in 1 second, and each car is 15 meters long. And the question is, well, what's the velocity of the train? Pause the video, do this on your own, and resume when you have your answer. So here's the solution. We have v equals distance over time by definition. Now the distance is 30 because 2 cars times 15 meters is 30 meters, and that's in 1 second. And so the velocity is 30 meters per second. Simple enough, right? Well, let's analyze it. 2 cars per second would be like a frequency if the train were a wave, and 15 meters would be a wavelength if the train were a wave. And so we've already kind of derived this formula for wave velocity, which is that wave velocity v equals f lambda. And it stands to reason with the train example, it's also true of any wave. All right, so frequency times lambda equals velocity. And this is called the wave speed equation. V equals f lambda. velocity equals frequency times wavelength. Now, this is the formula you need to know, but the next couple of steps are just going to be useful in a derivation that we'll do a little bit later in the video. So if E equals F lambda, then S over T equals F lambda, because S is just displacement, T is time. Velocity is displacement over time by definition. And if that's true, then S over lambda T equals F, just by dividing each side by lambda. And so this will be used in a future derivation. But of course, for this screen, the only formula you should highlight is V equals F lambda. Let's look at an example of wave speed. You may have used a 900 megahertz cordless phone. These waves travel at the speed of light, 3 times 10 to the 8th meters per second. What is the period and wavelength of these cordless phone waves? So pause the video, try to figure this out on your own, and then resume when you have your answer or if you get stuck. Alright, to get the wavelength, V equals lambda F lambda, same thing. And so 3 times 10 to the 8th meter per second equals lambda times 9 times 10 to the 8th hertz. Now why is it 9 times 10 to the 8th? Because we had to convert megahertz into hertz, and since 1 megahertz is 10 to the 6th, well, then 900 of that would give us 9 times 10 to the 8th. And therefore lambda is 0.33 meters. Now, to do the other part of the question, right, the other part of this example problem, to get the period, well, that's a little easier because period t is always just 1 over f. And since they give you the f, it's just 9 times 10 to the 8th hertz, then the period is going to be 1 over that. All right, so we can see that it's fairly easy to get the period with these givens. All right, now let's derive a general equation for waves. To do that, first we have to keep in mind that there is a relationship between uniform circular motion and the sine wave, just as there is a relationship between uniform circular motion and simple harmonic motion, as we saw in chapter 10. So let's look at some animations that display the relationship between uniform circular motion and sine waves. Here, a point is going to move around the circle, and as it moves, it's going to trace out its height, because the point has a height. Now notice that the height, AC, matches the height of that moving point E as we go along. The height of AC matches the height of the moving point E, and the moving point E, sure enough, is tracing out a sine wave. Or look at this example. P is moving around, and we see the height of P at all times. And P is moving around in a circle, going through a certain amount of radians. If we turn that around, we see that that P is tracing out vertically this sine wave pattern. Notice also, recalling chapter 10, that P is oscillating up and down harmonically. And that again helps us to remember the relationship between circular motion and harmonic motion. So circular motion is related to harmonic motion and to sine waves. And this animation shows all three concepts together: uniform circular motion, simple harmonic motion, and the harmonic wave or sine wave pattern. Recall from the last lesson that S equals A cosine omega t for a harmonically oscillating object. And you should refer back to your notes for this proof. And your notes should be organized all in one place, one binder. Anyway, S equals A cosine omega t. And the S that we're talking about is, if you look at this point Q, just as we saw in the last chapter, this point Q is like a shadow directly underneath P. And so as Q oscillates harmonically from right to left and then back again, so basically following this horizontal pattern that I'm tracing now with the mouse arrow, it is acting as a shadow directly underneath P as P goes around the circle. Alright, so that's just review from last chapter. And so the s that we're talking about is this distance, OQ, the distance from the center O to the point Q at any time during the simple harmonic motion is s. And that's given by a cosine theta, which is the same as a cosine omega t, as we saw in the last chapter. Now, why a cosine theta? Because if this is my right triangle, the triangle OPQ, well, theta is the angle there, the acute angle, and A, the hypotenuse, times cosine theta gives me this adjacent side OQ. All right, so we're going to use the same exact logic, the same exact trig to figure out what the heights are going to be. And as we saw in the last animation, if we can get an expression for the height, then we're also going to have an expression for the wave height, because the circular motion is intimately linked to the sinusoidal motion, or the sine wave motion. So it follows that h equals a sine omega 2. All right, so the h that I'm talking about here is going to be the line segment PQ that I'm tracing now with the mouse arrow. And we can see that if OQ was a cosine theta, then PQ is a sine theta. And theta is just omega t. And I don't need to do a proof for that because it's in your notes from last chapter. H equals a sine 2 pi ft because omega equals 2 pi f, as we saw in chapter 10. And h equals a sine 2 pi s over lambda tt. And that's simply from one of the previous screens in this chapter where we proved that f equals s over lambda t. And that comes from the wave speed equation that we learned earlier. And so now just simplifying, h equals a sine 2 pi s over lambda, and we're left with h equals a sine 2 pi over lambda s. This is the wave function, and this tells us the height of a wave when it is a horizontal distance s away from the origin. All right, I'll say that one more time. The h tells us the height of the wave when it's a horizontal distance s from the origin. We won't have an example problem in this video using this equation, but there will be something in the classwork that uses this equation. And here's a simple graph of the standard harmonic wave equation. Wave interactions. What happens when waves hit each other? How do waves combine? What happens when waves hit a boundary? Okay, let's see what happens when we have these two waves, small one on the left, big one on the right, cross. Well, you see what happens. They actually go right through each other. While they're going through each other, though, they reinforce. All right, so waves go through each other, but they do interact. And that interaction is called interference, as we're going to learn. Okay, so they're going through each other now, pass right through each other, build up right at that central moment. They build up and reinforce each other. And so basically what you have is the combined wave is a sum, the amplitude is a sum of the amplitudes of the two smaller waves. The principle of superposition. At the point where two or more individual waves meet, the displacement of the medium is the sum of the displacements of the individual waves. Individual waves are not changed by passing through each other. All right, so let's look at the first part of this principle. We know that they are moving together, and when they meet, the total height, which is large, is a sum of the two smaller heights. So we say that total height, the large one, and it's just what we get when we add up the two smaller heights. All right, so that's the first part of the principle of superposition, of how waves combine. The second part says that the waves simply pass through each other. Look at this. They passed right through each other. All right, and so even though there was an interference when they hit, in the end they pass right through each other unaffected. Now let's talk a little bit more about interference. And interference is interesting because it just means what happens when two waves combine. All right, so the principle of superposition tells us that A plus B equals wave C, this purple wave at the bottom. Okay, so interference just tells us that you can have two waves reinforcing each other or canceling each other depending on the motion. Okay, so look, now they're reinforcing, now they're canceling, now they're reinforcing, and now they are on their way to canceling. Okay, so let's take a more in-depth look at this. Okay, so at this point we have total cancellation because a trough of A is running into a crest of B. And so the two waves A and B are kind of canceling each other out so that C is a flat line. All right, and this also happens if crest meets trough or trough meets crest, whether you're talking about the top or bottom, that happens. Now, the opposite can occur when crest meets crest and trough meets trough. And notice when that happens, you're going to get the opposite effect. And that is that A and B reinforce each other to make a bigger wave C. So the effect of two or more waves traveling through a medium is called interference. Constructive interference occurs when two waves combine to produce a wave of greater amplitude than either wave. And destructive interference occurs when two waves combine to produce a wave of smaller amplitude than either wave. Now, what happens if a wave hits a boundary? In this case, the wave is going to hit a fixed point at the right. So let's see what happens to that wave. All right, it's going to move from left to right, hits the boundary, bounces back, but notice what happens when it bounces back. Let's look at it again. It gets reflected down. All right, so this is how wave reflection happens at a fixed boundary. There's an inversion, which we call a 180-degree phase change. Now, when a wave is reflected from a less dense medium, such as this unfixed point to the right, there is no phase change. All right, so let's see what that's going to look like. Wave comes, point goes up, and comes back. So there's no phase change, there's no inversion. It just bounces back as if nothing happened. And so that's what happens when a wave hits a less dense medium, or if you want to envision it, a point that's not fixed. One more time, look at it, and comes back, unaffected. Okay, so let's look at something that's called a standing wave. And first of all, let's envision two waves that head towards each other on the same medium, and look at the interference pattern. All right, the interference pattern makes it look as though the two waves, one moving right to left, the other moving left to right, it looks as if one thing is standing still and vibrating in place. In fact, what we have here is two waves moving together. So a standing wave is produced by the interference of two periodic waves of the same amplitude and wavelength traveling in the opposite directions. All right, and so that's a standing wave is a name for this interference pattern. So they hit each other, and now we have kind of in lighter dots the two waves still moving. All right, we still have the right-left wave and the left-right wave, but in the solid blue dots we have their interference patterns, which gives us this illusion of the medium just oscillating or vibrating in place. This is what we call a standing wave. The most common example of a standing wave is the string of a musical instrument, as we shall see later. Now, in standing waves, we have certain points that have names. So look at these red arrows. Look at the pattern of the standing wave, and notice that at the tips of the red arrows, it seems as if the medium is stationary. All right, that's the visual effect. Let's look at that again. The waves hit each other. We're seeing the background waves this time, the standing wave that seems to stay in place, and the red arrow points appear fixed. And the points in the standing wave that do not move as waves pass through each other are called nodes. That's just the name for them. They're called nodes. Now let's look at the waves coming together again, standing wave. And let's look at these blue arrows. These blue arrows, notice, are pointing at the points of maximum oscillation when the standing wave seems to be moving the most. And those also have a particular name, the points of maximum motion. And so they're called antinodes. Points where the displacement of the medium are largest are called antinodes. All right, this brings us to sound. We've talked about waves, and one of the prime examples of a wave is sound. So here's an animation of a sound wave. On the left, we have a speaker vibrating, and it is compressing the medium, air molecules. And those compression waves are traveling along the medium. However, if you look at those little red dots that kind of highlight certain molecules, as the oscillation happens, you'll see that the red dot basically stays in place. It wiggles back and forth, but it doesn't travel the whole length of the wave. Energy is transferred through the medium, not the particles. Now here's what sound waves look like. You have points of compression where there's maximum pressure, and you have points of rarefaction where there's minimum pressure. And if the high pressure corresponds to a high wave height, then that would be a crest. And if the low pressure corresponds to a low wave height, that would be a trough. And that's why we have this sine wave underneath the longitudinal wave. This is just to help us visualize that this longitudinal wave does act like a transverse wave. It's just that the orientation of the oscillation is different. Frequency in sound is called pitch. When the frequency of a sound wave is changed, we would say there's a change in pitch. We're used to this when we hear music. People can generally hear from 20 hertz to 20,000 hertz. That's our range of hearing. Amplitude in sound is loudness. If a sound wave has a greater amplitude than another sound, we would say that it is louder. All right, so in terms of a sound wave, this is how frequency and amplitude work. Audible and inaudible sounds. All right, so all vibrating bodies produce sound. The classification is based on the sound frequency. Let's say we look at a table of frequency and audibility. Well, 20 hertz to 20,000 hertz would be the sounds that we frequently call audible. Sounds of such frequencies are called sonic. They are audible to the human ear, so it's just a term for them, sonic sounds. Below 20 hertz, we have infrasonics. These are, of course, inaudible to the human ear. And then once we get above 20,000 hertz, we're dealing with what they refer to as ultrasonics. And you've probably heard these terms before. We have infrasonics, we have ultrasonics. What we're used to hearing, of course, are the sonics, or the simple audible sounds in the range of 20 hertz to 20,000 hertz. So infrasonic waves are produced by earthquakes and storms in sea. Ultrasonic waves can travel longer distances without undergoing much change in their properties due to their low wavelengths. For example, to find the depth of the sea, we use ultrasonic sounds. You've probably heard of it as sonar. And the fact that these ultrasonic sounds can travel so far is helpful for this use. Ultrasound can detect tumors in the body. As you know, it's also used to see fetuses in the womb. It can be used to study heart valve action without invading the heart. It can be used to treat cancer. And it can also be used to locate cracks and faults in metal castings. If they're going to build a skyscraper, for example, they need to make sure that the metal girders are without defects, and so they can do ultrasonic testing on all of the metal. The speed of sound varies directly as the density of the medium. The denser the medium, the faster sound travels through it. And that's because the particles of the medium are closer together, and so they're able to transmit longitudinal waves more quickly. Let's look at some of these values here in the table. A standard value for the speed of sound is its speed at 0 degrees Celsius, 331 meters per second. I prefer to use 343 simply because for most problems and most of our experience of sound, especially those of us who live in California where it's fairly warm, would be around 20 degrees Celsius, which is about 68 degrees Fahrenheit. And so 343 is better as a rule of thumb if you want to think of how fast sound travels. Um, and then, of course, the speed of sound in different gases and in water. Now, you can see that sound travels much faster in water than it does in air. And sound travels very well in water, which is one of the reasons why if you go fishing, those of you who like fishing and you're in a boat, you don't want to be banging things around in your boat because that scares the fish away. All right, and then if you look at speed of sound in solids, they transmit sound even better. Supersonic means faster than the speed of sound, and the neatest effect of supersonic things is the sonic boom, as we're going to see next.
Sound travels at about 760 miles per hour, or 340 meters per second. That's about 661 knots on an average day at sea level. And sometimes you can almost see it. Going close to that speed through air can cause some unusual visual effects. What you're looking at here is a NASA image of an SR-71 bending light waves from the pressure differentials it's producing. Air's pressure and temperature both drop when airspeed increases. Rapid changes in density can be enough to bend light like a lens. How does it happen? Airspeed increases as it flows over the form of an aircraft pushing its way near Mach 1, the speed of sound. That means that even aircraft slower than the speed of sound can accelerate the air moving over them beyond the speed of sound. As pressure all around the aircraft drops, that air cools, and as air cools, its ability to hold moisture drops. So if there's enough moisture, you'll see it form in clouds that appear attached to the aircraft itself. But the cone-shaped clouds you see aren't in fact traveling with the aircraft. Each section of air is spontaneously reacting to the temperature and pressure change induced by the aircraft's body sliding past. Then there are the shock waves. Shock waves are formed by the air that can't get out of the way fast enough, forming a pressure wave. We perceive that pressure wave as sound. Aircraft actually usually produce two booms. They just reach us so quickly in succession that we can't distinguish the two. All of these factors are quite normal and have come to be expected in images that capture supersonic, transonic, or even near supersonic flight.
Sound intensity. The intensity of a sound is the amount of energy that passes in a given time through a given area. So remember that wave energy depends on amplitude, and so loud sounds have more energy. But let's put this in terms of equations. So you can see we have energy going through a certain area per unit time. So E over T over A, just energy per unit time over area. And that brings us to intensity equals power over area, because energy over time, or joules per second if you want to put it in units, is power. All right, so intensity of sound, or any wave for that matter, is power over area. This is a definition. I'm highlighting it because it's one that you'll need to use in problems. But it really isn't a formula, it's just a definition. And I know that sometimes it's irritating when they use the same letter to mean a bunch of things, because we've used I to mean impulse, and we've used it to mean moment of inertia. Well, here it means intensity. So just like often happens in language, the way you tell them apart is from context. Now, bats can use sound intensity to locate small objects in the dark, and that's pretty neat. They are able to emit ultrasound or ultrasonic waves, and when they do so, what happens is that their brains can distinguish the different intensities and see if something echoes back with a high intensity, then it's close. If it echoes back with a low intensity, then it's far. Sound intensity from a point source will decrease as the square of the distance. All right, this makes sense first of all because we know that if we're close to a sound, it's a lot louder than if we're very far, and if we're extremely far, we can't hear it at all. All right, so we have experience with this. Now, this is called an inverse square law, and it just means that something varies inversely as the square of another quantity. We've already seen this with gravity. Remember, uh, the force of gravity equals g m1 m2 over r squared. And so gravity gets weaker and weaker as things get farther and farther apart, and it varies inversely as the square of the distance. Well, sound is the same way. All right, so this definition looks like this. I equals P over 4 pi r squared. Now, don't worry, this isn't going to be some kind of big formula to derive. It's actually a lot simpler than that. We already know that I equals P over A from the last screen, and that's just by definition of sound intensity. And now the reason we're replacing A with 4 pi r squared is because that's simply the surface area of a sphere. All right, so if a sound is made, imagine an explosion in the sky. Well, that sound is going to go in 3 dimensions um, all over, up, down, all around, in the shape of a sphere that keeps radiating outward. So that's just how sound works. It's a longitudinal wave, but it extends as a sphere in all directions. All right, and so the surface area, the A of a sphere, is 4 pi r squared. It's just a formula for the surface area of a sphere, just as, you know, pi r squared is the area of a circle, or 4/3 pi r cubed is the volume of a sphere, etc. All right, so this is the intensity of sound as a function of of the power and of the distance from a point source. All right, I equals P over A with 4 pi r squared as A. Intensity level. A sound that seems twice as loud as another is 10 times more intense. All right, we sometimes think of loudness and intensity as the same, but they're not. They're related, but they're not the same. All right, so something 10 times more intense is twice as loud. Now, for convenience, we use a logarithmic scale to define intensity level, and that's because if we use the linear scale, we would end up with huge numbers in the billions for very loud sounds and extremely tiny numbers for soft sounds. So the logarithmic scale just is more convenient. It keeps the numbers lower. So the definition of intensity level, beta, again, this is not a formula, this is just a definition, is beta equals 10 log I over I0. And I'm going to explain what this means in just a little bit. The SI unit is decibels, and actually the bell is named after Alexander Graham Bell, who did research on sound, and the decibel is just 1/10 of a bell, but it's much more common than the bell. I0 or I sub 0 is the faintest sound that can be heard, so it's sometimes called the threshold of hearing, and that's tiny, 10 to the negative 12th watts per square meter. And so this is the definition of intensity level. Now, a change in intensity level, or delta beta, is given by delta beta equals 10 log IF over II. All right, now this comes really just from properties of logarithms, and any of you who are interested, I can quickly go through that derivation in class. But since that's based on math that some of you might not have had yet, I'll just leave it at that. You can ask me and I'll answer it. But delta beta, or the change in intensity level, when you're talking about one sound versus another, is 10 log IF over II. All right, so the definition is always comparing a sound to the threshold of hearing I0, whereas the delta beta formula, change in intensity level, is comparing one sound to another. This is a little chart that shows that shows loudness in terms of decibels. Now, if we are looking, for example, at heavy traffic versus the passing of a subway, so 90 or 100, well, on the decibel scale, which is logarithmic, that's a difference of 10 decibels, but that actually means that the subway passing by is twice as loud. All right, and then thunder would be twice as loud as the subway, and the rock band would be twice as loud as the thunder. That's just how logarithms work. A small change in a logarithmic scale equals a big change in a linear scale. Again, don't worry about all the math behind that if you haven't had it yet. So if you look at where the eardrum ruptures, that's an extremely loud sound. And you start to feel pain at 130 decibels, which isn't that much louder than being at a typical concert. Especially if you're in the front rows. If you're in the front rows of a concert, you could be exposed to decibels that are significantly beyond the pain level. Let's look at this problem. You're standing in the 10th row at a rock concert, 15.0 meters from a 1,000 watt speaker. What is the intensity of the sound you hear? What is the intensity level? All right, now remember, intensity is going to come from your definition for intensity, but intensity level, that's your beta. Okay, intensity is not the same as intensity level. Intensity is a physical reality. Intensity level is just something decided on by human convention, which is beta. All right, so pause the video, answer these two questions, and then resume when you have your answer. Let's go through the solution. So I equals P over 4 pi r squared. That's our formula. We put in our givens of 1,000 and 15, and we end up with 0.354 watts per square meter. That's our intensity. Now, what's our intensity level? Beta equals 10 log I over I0, and so that's 10 log 0.354 over 10 to the negative 12, and that's 115 decibels. That's quite loud. Now let's look at part 2 of the sound intensity problem. Your friend is standing in the first row at the same concert, 5 meters from the 1,000 watt speaker. Between the first and 10th rows, what is the difference in the sound intensity level? How many times louder is the sound in the first row compared to the sound in the 10th row? All right, so for the second question, you're just going to use that chart and remember about the doubling thing. But for the first question, you'll use some formulas. So pause the video, do this on your own, and resume when you have your answer. All right, let's go through the solution. So first of all, you have to figure out what the intensity is of the sound that your friend is exposed to. And so that's just P over 4 pi r squared. And now the R we're going to use is 5 instead of 15. And so that's going to be 3.18 watts per square meter. That's extremely intense. And now we can use our delta beta formula. So 10 log IF over II. And normally what you do is, well, you can always consider anything your final or initial, but you should consider your initial just because it's standard. The initial is the smaller of the two, and the final is the larger. All right, so we have 10 log 3.18 over 0.354, and that gives us 9.53 decibels. Now that looks like a small difference, but it's not because it's a logarithmic scale. So remember that a difference in 10 on the logarithmic scale means double the loudness. So that's about twice as loud. The sound that your friend in the front row is exposed to is twice as loud as the sound that you're exposed to in the 10th row, and that's downright bad for the ears. All right, that's almost you could almost say that's abuse of the ears. And anyone who goes to a significant number of concerts and stands in the front row or even stands in the 10th is eventually going to lose their hearing. Okay, let's go back to our discussion of musical sounds. So pitch is the highest or lowest sound an object or instrument makes. The higher the frequency or pitch, the shorter the wavelength. And this should make you remember what I said earlier, that a high frequency goes with a low wavelength and vice versa, low frequency with a high wavelength. All right, so this is also true in music. And musicians give the different pitches different letters in a piano keyboard. What we just heard was an entire octave. So let's talk a little bit about octaves. A factor of 2 increase in frequency is called an octave. So 440 hertz to 880 hertz, for example. Listen to these notes. So standing waves on strings. When you pluck a string, like say you pluck a guitar string, you're setting up a standing wave because waves are going in either direction, but this interference pattern, as we've seen, sets up a standing wave, and that creates a sound. The speed of a wave is determined by the properties of the material through which it propagates. All right, that makes sense. Um, for a string, the wave speed is determined by the tension in the string and the density of the string. All right, so you can imagine that if you have a really tense string, it'll make a different frequency than if you have a really loose string. And if you play the guitar, you probably have noticed that. And also the thickness or density of the string matters as well. You know, the thicker string produces a lower sound in general than a thinner string. So as the tension in the string increases, the speed of waves on the string increases as well. As the density of the string increases, the speed of waves on the string decreases.
So we can express all of this in the mathematical formula V equals square root T over M over L. T represents the tension, and M over L represents the density of the string. It's just mass per unit length. So that's the string density. And here we see the direct relationship between velocity and tension. And we also see the inverse relationship between velocity and density.
Standing waves on strings, looking at a specific instrument. All right, so if we look at this guitar, and don't worry about those little notations about the octaves. We'll learn more about that in a second. But the main thing for this screen is that in order for different strings to have different fundamental frequencies, they must differ in length and or density. So on a guitar, the string lengths are all the same, but the density or string thickness varies. And that is what results in the different tones, that along with the tension.
So if we look at this diagram of a string, notice that if you pluck a string, the center is going to be going up and down, oscillating, whereas the ends will remain fixed. But notice also that this shape is half a wave. A true wave would start in equilibrium, go up to its maximum, come back to equilibrium, go down to its minimum, and then go back to its equilibrium. Now, that doesn't happen here. You can see that it's only half of that pattern. That's why we would say that the length of the string is lambda over 2. It's half a wavelength. So for the fundamental, lambda equals 2L. Now, the fundamental just refers to the overall tone of the string, right? If you pluck an A string, you'll hear an A note, although there may be other harmonics and overtones that give that particular instrument its flavor or timbre. But the fundamental is the main thing you hear, and that's lambda equals 2L. Now, since V equals F lambda, as we've already seen, we can then fill stuff in, and we get the expression root T over M over L. That is V, and that V divided by lambda gives us F, and we've plugged in for lambda 2L. So this is the main equation when we're dealing with frequencies of standing waves on strings.
In a piano, the strings vary in both length and density. This gives the sound box of a grand piano its characteristic shape. So you've seen that curved shape before. The strings have different lengths and different densities. Once the length and material of the string are decided, individual strings may be tuned to the exact desired frequencies by changing the tension. All right, it's pretty hard to change the density of a string or the length, but you can easily change the tension because those instruments or those means of adjusting tension are built in to the musical instrument. Musical instruments are usually designed so that the variation in tension between the different strings is small. This helps prevent warping and other damage, which means that you don't need extreme amounts of tension to produce sound. Just moderate amounts. If they required extreme amounts, then they would probably the frame of the instrument wouldn't be able to withstand it. All right, here's just a quick thing. If you're interested in this, you can look at it for a little bit. If you're not, you can skip this slide. But it's for those of you who play the piano or are just interested in music, it's kind of neat to see this. This is all 88 keys of the keyboard, and the other columns indicate the exact name of the note and the exact frequency of the note. Now, probably the most important note of all, well, two really important notes. You've got middle C, and that's over here that I'm highlighting now with the mouse arrow. But even more important than that is A440 or A4, all right, because it has a frequency of exactly 440 hertz, and it's used as a standard, especially used in tuning instruments as a standard by which to measure all other frequencies. So A440 is important as well. Also notice another neat little thing. If you start at A440, for example, one octave above that is A5, that's 880, and one octave above that is A6, 1760. Notice how when you go up an octave, you double the frequency. Now the way that standing waves on strings actually work is pretty interesting. We call this harmonics, all right? So let's say we have a table of a harmonic wavelengths and number of loops in the string. It turns out that standing waves on strings include many different kinds of waves at the same time, all right? So the first harmonic, or the fundamental, carries the note. And so that would correspond to half of a wavelength bouncing up and down. But on the same string that's vibrating with the first harmonic, it's also at the same time vibrating with a second harmonic, which has a full wavelength, and that carries a different tone, what is called the first overtone. That doesn't conflict with the fundamental. And then we have the third harmonic, which has 3 half wavelengths, and so on. And so as a string vibrates with the fundamental or first harmonic, it's also vibrating with the other harmonics, and this gives an instrument its distinctive sound. All right, the number of overtones that an instrument has, and also the proportion of those overtones to each other, gives instruments a different sound, so that an A440 note on a violin sounds different from an A440 note on a piano, which sounds different from the A440 note on a guitar. And that is what gives instruments their flavor, and this flavor is known as timbre. Timbre is the distinctive flavor that an instrument has.
Let's talk a little bit about Chladni plates, which are interesting. Chladni plates show standing waves on solid flat surfaces because standing waves don't only exist in strings. Chladni plates were developed by the German physicist Ernst Chladni in the 18th century, and his work with Chladni plates earned him the title the father of acoustics. What he did is he put some sand on flat metal plates and drew a bow over the plate in order to get it vibrating, and was able to see patterns because the sand would gather in the nodes of the standing waves that formed on the plates. Let's see a quick demonstration of Chladni plates and Chladni figures.
The Doppler effect. The Doppler effect is the perceived change in pitch of a sound when the source and observer are moving with respect to each other. When an observer moves toward a source, the wave speed appears to be higher and the frequency appears to be higher as well. All right, so let's look at this example. We've got a skateboarder and he's riding towards the stereo, and it's a stationary source of sound, but he's riding towards it. And so um, the uh, the waves are actually getting to his ears faster than they would if he were stationary, and that's why it seems to make the frequency higher and the wave speed higher. The Doppler effect from a moving source can be analyzed similarly. Now it is the wavelength that appears to change. Right, so when the source of sound is moving, then the waves are kind of getting bunched up closer together. And so if you have a shorter wavelength, you also have a higher frequency, and that means a higher pitch. And that's how the Doppler effect works. It's a perceived change in pitch because of a moving source or a moving observer. This is a little model of that moving source of sound. As you can see, in the direction of motion, the waves get bunched up, and opposite the direction of motion, the waves are spaced farther apart. So that affects the sound frequency. In front, you're going to have a higher perceived frequency, and in back, you'll have a lower perceived frequency. Some Doppler effect applications. The expansion of our universe was discovered with Doppler-shifted starlight from distant galaxies because as those galaxies depart from us, they look reddish, and that's because their perceived frequency has been shifted down to the red portion of the visible light spectrum. It's also used to estimate the speed of vehicles through shifted radar waves, and that's not good news if you get a speeding ticket, because what cops use is a Doppler effect radar to track speed. And it's also used, Doppler radar is used in weather, meteorology, as we're going to see in the next screen. At left, the Doppler radar shows the hook echo characteristic of tornado formation. So let's look at this. If you look closely, you can see a little hook shape here curving around, and you can see another little hook shape towards the bottom right of the circle. And the way Doppler radar works is they send long-range microwave signals into these winds. And based on the echo patterns, they can tell how fast the wind is traveling, and when it forms that hook shape, they know that the fast winds are about to curve into a tornado. A Doppler blood flow meter uses the same principle, but with flowing blood, and the speed of the blood will affect the patterns of echo that get reflected off of the blood.
Here's the classwork. Please write these numbers down, which would be posted in a worksheet. See you in class.